My name is Gregor. I work for marketing department, Aerohive Networks. I'll be talking about the CCI today, or CCC, or whatever you want to call it. I actually conjured a new name for it because I guess this is a thing that we do in marketing. So for those that don't know me, I work for Aerohive Networks, marketing knowledge services department. And within knowledge services department, I have a simple and easy job. So what I do is I make coffee. It's an important job. So there's various reasons for me making coffee. First, we interact a lot with engineers. Our engineers trying to learn how our stuff actually works. So to make them relax, but still thinking and interacting, right? Coffee is important. And then also my boss, he's like 120 years old. So coffee makes him start thinking and interacting again. So that's my forte. So let me just start with sharing my desktop. And we'll start with the presentation. Okay, so CCI in depth. We have an hour. Actually, we have now 50 minutes, which is not nearly enough to take the CCI in depth. So I'm making this in CCI digest, right? You'll see the components and everything involved, and it gets pretty complex. So I think that digest is a better word for it. Especially as you have a couple of other presentations that will go in certain topics in more detail, but this will be like bringing everything together. And just because, as I said, the naming convention, CCI, interference, a lot of people don't like the interference in the end, they like the contention. I just say that I don't like the CCI or the CCC, so I'm just calling it the dude effect. Okay, so today we're discussing the dude effect. I'll just start with a couple of acknowledgements. A lot of this information has been stolen from smarter people than myself. The reason being is, well, I just didn't spend a lot of time creating this presentation. This presentation has been, well, created for the WLPC in Europe. I haven't touched it since, so I just steal from these smart people, starting from our Matthew Guest. He's also in our marketing department. David Coleman, he's that 120-year-old dude I have to brew the coffee for. And also we have... well, Andrew, right? He's stealing the audience. I guess he has the full room, so I'm stealing his stuff as well. Ben Miller, I think he's there, and a couple of other stuff. So if you want to go even deeper into what I'll be presenting, those are very, very recommended resources. On top of it, of course, there's always a standard. Personally, I don't like reading the standard. I cannot understand half of it. So this is just a more convenient way of understanding what's going on in Wi-Fi. So what is code-channel interference or code-channel cooperation, contention, whatever you want to call it? Right? As we all know, Wi-Fi is a half duplex, contention-based communication on the medium. And to make it work, there's one simple rule. Right? Only one station can communicate at any given time. It's a shared medium. It has to have an order, right? One talks, everybody else listens. For this to happen, there is a simple process to it. Before starting the communication, you have to go through a couple of processes, starting with both physical and virtual carrier sense. One is on the physical side, the one is on the layer 2, so the MAC side. If you pass both, you go and observe the appropriate interface spacing interval, followed by a backup value. and all of that. If everything is okay, everything is checked, you're ready to go. If something gets broken in this process, you go straight back to the start and start again, right? So this happens for every frame exchange and for every station. And the thing is where, yeah. We're back? Yeah, sure. Yeah, I've started again. Can you see it? Okay, good. Can you see the presentation now? Okay, perfect. So everything has to happen in order for every station to transmit on the media. Now, in between the physical and virtual carrier sense, one is much easier to understand to the common engineer because it's much more tangible. This is the layer 2, it's the MAC, right? It's simple to grab MAC information. It's simple to see it in your Wireshark, you OmniPeak, or whatever frame capture and analysis tool that you're using. You know where the nav timer is, and you know how it looks like, right? It looks like this. Virtual carrier sense in a duration field, which has a couple of other purposes, but one of the most important is the nav timer. Once a station listens and looks at the duration field, it will set up the nav timer and start that counting down, right? And everything is fine. We can see it. We can understand it. We know how to plan our network for it. We know how to adjust the capacity. And overall, we're a happy camper, right? Because frames don't lie, right? Everything that you see in frames is the truth. Well, not necessarily, right? The virtual carrier sense on the Mac is straightforward, is easy to understand, but it's the physical that's a little more, well, more difficult to understand, right? You don't see it. In the frame capture, when you're looking at the radio tab, that's not your physical carrier sense. That's just information from the driver. Hopefully, it tells what it is. Sometimes it's not a good interpreter. So let's just walk from to the process of how and where the physical carrier sense engages. I like this process because it's complicated. Right? It makes me look smart. So I'll just use a couple of minutes to go through it. As a reference, here is your Mac, right? On the left-hand side of the slide, this is where the nav timer, so the duration field is. This is where you can see what is happening. So let me just walk you through the process then on the physical layer. So the Mac has to be prepared. In the preparation of service field, it's prepended to the transmission that it's gonna send out. The main component of this is CRC calculated for the signal for the preamble. Then we have the phi padding, just to ensure that we have a proper length of the phi, so everything goes through. We have the scrambling and forward error correction encoding. It's basically what it does. It reduces the probability of the long strings, so identical zeros or identical ones, because the convolutional codes work best if you don't have the long runs of those identical bits. So it just does its magic. Continues to the stream parsing, which takes the output of that FAC encoder, divides it up in coded bins, and divides it for each spatial stream, right? So if you have two spatial streams, the stream parser will divide it up to the encoded bins and assign them to each one of the spatial streams. The segment parser, this is an interesting one. I believe that you also have the presentation about the AC, so you'll hear about that in more detail, but this is where the AC 160 megahertz blocks can be divided into 80 megahertz blocks, and they are not tied together, right? So you can map them into two different frequency segments. That may happen if you use 80, 40, or 20 megahertz channels. That doesn't happen. Anyways, for each segment, or for just 20, 40, or 80 megahertz transmission, you're getting convolutional code interleaving. It's where the errors are isolated so they can be better repaired on the receiver side, and a lot of mathematical magic happens here. Constellation mapping, where you take all of this nice data and map them to OFDM subcarriers. Segment parsing, segment deparsing, again, bringing that all, if you do 80 megahertz in two blocks, bringing them together. Optional space-time blocking, pilot insertion, spatial mapper, inverse Fourier transfer, where you take the frequency domain to the time domain, guard intervals, right? Let's make it fast, click the short guard interval and make it happen. And then, boom, this is the physical, right? This is where the preamble is constructed. And then you end up with the RF magic going out of the antenna out. So if you look at it from the reverse angle as a receiver, you can see that just behind the analog and RF component, there is the preamble detection, right? And all of that stuff, which is extremely complicated, happens before the MAC, happens before the timer. So once you figure out that, yeah, I can read the MAC address, but all of that stuff comes before, if you're not careful and introduce that realization into your design, you'll end up like this. And that's a sad state to be in. Physical component is important. It's extremely important to Wi-Fi. Actually, it's extremely important to everything you do. Right? So let's try to understand the physical component a little bit better. Right. So the physical component uses carrier sense directly on the physical radio interface. Virtual carrier sense uses the duration value and the MAC header. We've been through this. Both are complementary, but as you can see, while that framework showed us that both are happening at the same time, obviously the physical happens before the virtual. To make things even more complicated, there are certain rules that we're following, and those rules are implemented differently based on the modulation. Starting with the legacy PHY, so your legacy 802.11, the standard alone introduces 3 possible modes of the detection. One was pure energy detect. So if you hear any signal that exceeds a defined threshold, you just hold off. Second mode is you look at the actual preamble, right? So we call that carrier sense. If you read the standard, you will find the word preamble detect. So carrier sense or preamble detection, it's the same thing. Personally, I prefer the preamble. So you have to know how to read it. You have to be able to read it and then defer, or the combination of both. So either a signal has to be detected with a sufficient energy, plus we have to read it. We have to be able to read it in order to back off, right? The second thing is, and it's similar to 802.11b, energy detects defined threshold. Mode 4 looks at the actual signal, so preamble detect, but also triggers an additional timer, which is counting down. So after the detection of the signal of the preamble, it triggers a timer, starts rolling around, and then if everything is idle, you can start transmitting. And mode 5, which is the combination of the two. Now, what has happened in the real-world implementation, with all of the different modes, the vendors just said, oh, heck it, right? I'll just do something that is kind of like this, but modified to be more optimal, fast, easier to understand. And you know what happens when you go outside of the standard, right? Not a lot of good things, which is why the standard committee has learned about this. So for the OFDM PHY, which is what you hopefully are using predominantly on the networks today, the standard was not as prescriptive, right? It uses the combination of the energy detect and the carrier sense. The carrier sense has to be at a level equal or greater of the minimum modulation encoding rate sensitivity. So for the OFDM, as an example, your 6 megabits per second should be able to be decoded at minus 82 dBms. The energy detect adds 3 dBs on this. So what you end up is, if you can read the preamble and the energy is at minus 85, you have to defer from the channel. And again, then you have still your pure energy detect, which is any energy detected with minus 65 dBms, it will also defer, right? So it's important to understand all of the three, because we're still using all of the three. Hopefully not the legacy as much, but your B and then G as in OFDM, or A as the OFDM, we're using that one. If you're thinking about, so what's the difference then with N or AC? Well, you're still using this one, right? So let's take a look at the layer 1 preamble. How does it actually looks like? So this is a combination of two options. The upper one is a long preamble. So we have a sync field, which was used just to get attention. It will say, hey, Chris. Is Chris paying attention? Okay, now I can communicate with you. So it's the same thing, right? It's a syncing, making sure that everybody is aware. And then the second part is the preamble, right? So the preamble actually carries information, signal service length. And within that signal, so this is layer 1, we have the information about the length of the whole frame, the modulation, so the speed that the frame will be sent at, and a couple of other information. So any station able to decode 1 megabit per second or 2 megabit per second in the short preamble will be able to understand, hey, there's something happening on the medium and I have to defer it, and I know for how much time, even if I'm not able to read the virtual carrier sense in the form of the nav timer. So we have the information of both, right? Layer 1 protection, layer 2 protection. Now, long preambles were very, very inefficient, to the point that, as you know, every sent frame has to have a preamble, and to the point of sending the unicast frames where they have to be acknowledged, the preamble was much bigger than your acknowledgement frame. Right? It just didn't make sense. So the implementation of the shorter and more efficient preamble was soon introduced. So it was introduced in 802.11b, and it's something that was turned on usually by default with most of the vendors. So what happens is we send 1 megabit per second for the syncing and 2 megabits per second for the preamble, and then followed by any modulation to 5.5 or 11 for our payload. Right? This has to be understood. It doesn't matter what data rates you're setting. If you have 802.11b, we're still on the B slide. If you have it 11 megabits per second or 2 megabits per second, it doesn't matter. The preamble, the training field is set at 1, and the signal, the preamble, is set at 2 megabits per second. If any station is able to decode this at -85, and you know that -85 and 2 megabits per second, oh yes, right? A lot of stations can decode that, and a lot of stations can decode that very far away. It doesn't matter what you set up as a data rate. So this, again, was optimized for the OFDM, then 802.11n, and of course, now the latest and greatest VHT mode in 802.11ac. So the OFDM has two ways. It was implemented two ways, one for the 802.11a, which obviously didn't have to take care of the protection mechanisms for the legacy clients. So it introduces just the the legacy short training field, long training field signature again, and this signature carries the information about the data rates, the length, and everything that the station needs to understand. I have to defer for that amount of time, and then the variable, right? So the training fields and the signal field, they're all sent as at the lowest OFDM modulation, which is 6 megabits per second, right? So it's much more efficient, and it doesn't carry as far, so you can make the cells more compact. But again, it doesn't matter what type of data you set at a variable, you'll always have this at a set as the preamble and the training fields. Now, 802.11n introduced a couple of different preambles. I'll talk more about them in the next slide, but the most commonly deployed is the HD mix mode. Right? So with 802.11n, as with anything that we're progressing when we're doing the new standards, the amendments to the standards, it has to be backwards compatible. So even 802.11a stations or G stations, they have to have a way to detect transmissions in order to defer from the channel so we don't make a mess. So we have our basic OFDM, legacy short training field, long training field, and signature, where you can read the data, and then everything else, right? AC is very similar to it. It carries additionally something called VHT SIG-A. While it's sent out with the OFDM, only AC can demodulate it. One thing that is interesting, though, this signature, you've probably heard it, and you've heard it a lot. Frames don't lie. Packets don't lie. Well, they do, right? And this one is the example of this. The legacy signal field was not created to carry information of all available data rates in N or AC. Plus, the old legacy A or G stations would not understand what your 300 megabits per second or whatever data rate means. So what happens is the signal field carries 6 megabits per second always, and then it spoofs the just the length in bytes of the following frame, right? So it's double lie. It lies about the data rates. It lies about length of the frame in bytes. However, the result of this, you can calculate the time that you have to defer from the channel, right? So your A or G stations will be able to see and say, okay, with 6 megabits per second and X amount of data, I have to back off for this amount of time. Right? If you are sniffing and capturing N or AC frames with G or any G radio, you'll still capture this, right? You'll see the radio tap information, and if your capturing device or your Wireshark isn't smart enough, it will show 6 megabits per second. Frames do lie, right? Everything lies. So once you have this done, you have the second part of it, which is in N, the HT modulation or AC VHT modulation, carrying the specific information that are much alike information in the duration field of the MAC frame. As for N, in standard, there are 3 modes defined, non-HT. So if an N access point was serving nothing but the legacy clients, it would defer. And as you can see, this is basic OFDM preamble. Mixed mode, which is what is most commonly deployed, where you have the first part that it's OFDM and second part that it's high throughput OFDM, so MCS 0. And the grid field, which is very rare, up to no existence, in a case that you would have nothing but N-capable stations in your ether, right? So while this is in the standard, the implementation is non-existent, very rare, so just B as a mixed mode is the only one. And AC followed the following standard, just has the mixed mode. So it doesn't matter what you do, even if you have the AC, you'll always have the OFDM preamble. Now I have to reiterate about the speeds. Whatever you do, 3 spatial streams, 4 spatial streams, 2, the 256 QAM, whatever the data rate is set, the preamble will always be set at the 6 megabits per second OFDM for the legacy and MCS 0 for the HT or VHT field. Right? So in addition to that, right, we still have the MAC layer protection mechanisms. So it just makes sense, right? If one fails, then you have the other that can kick in. And this is your typical clear to send before you're sending the frame, or even the request to send, clear to send operation, plus the information in both beacon frames and probe responses that can tell the Wi-Fi devices you have to engage the protection mechanisms because there are other legacy clients in the ether. Not always guaranteed to work, right? Because real life is real life. But this is why we have the different modes of protection mechanisms just to make it work, right? So knowing all that, what can we do to improve to reduce the code channel interference? Number one is plan and deploy 802.11ac. And the reason for this is not just, hey, it goes faster, multi-gigabit, shiny new dual quad-core processors and everything that. It's one special feature that makes the optimization on the layer 1, and it's a MPDU. So aggregation of MPDU to have more MAC layer frames put together and send out with just one set of preamble, right? So reducing the amount of frames automatically reduces the contention that is created with preambles. So this is why the AC is recommended. The second thing is you also have to understand the device-specific behaviors, right? We all know that while the standard is somewhat, sometimes very prescriptive, sometimes not so much, the device tend to behave differently. One example that I liked, and it was done by Ben Miller. I do recommend his blog, by the way. So if you go in, he always has interesting stuff. So there's a blog about behavior of the iPad 3 versus the iPhone 5. Obviously, this is a little bit older blog, but still you'll see there's a difference of the behavior of the clients based on the physical properties, right? One of them is iPad 3 started sending probe requests at a certain level, and once it still hadn't connected to the station, it upped the TX power to more. Why is this important, right? The more TX power that we have, the further our preamble, well, I guess fly or will reach or whatever. So our CCI contention domain will be bigger. Just the opposite of this, the iPhone 5 started at a certain level of the TX, and after it was not associated for a while, it began lowering the TX, right? Just different behavior. Now, once you think about it, it kind of makes sense. iPad carries a bigger battery, long battery life. It can afford to give more power to the radio in order to connect. iPhones, right, they're getting better with the batteries, but it's not superb, right? It just cares about the battery life more than the connection itself, right? So knowing the client behavior will be influencing your PHY design much better. The second thing that you have to understand is it makes you dizzy happy. The closer the devices are to the access point, they seem to react better in sending less of probe requests, less of overhead, less of frames being sent out, the less of contention interval. So, and then the next thing is...
Oh, God, this presentation is so boring.
It's the most boring thing I've ever heard. It's horrible. It's horrible.
Oh,
okay, guys.
Man.
Guys, I guess I have to introduce a couple of people, couple of jokesters here. So please welcome David Coleman, my boss. And please welcome Brian Harkins. So let's just do this for introductions. That's because I make good coffee. Right? So I guess my presentation is boring, so they'll help me make it a little bit better.
You're doing just fine.
Yeah. So let's talk about how we can improve our CCIE, right? So one thing is just use the environment. You've had a couple of good presentations already. There's a lot of things that you can use with the high density environments. Obviously, the contention is very important in those. And I would not just stop there. To use the environment, I like to create the environment, right? Because there is just so much that you can do with the existing environment, right? You can be careful about the positioning of the access point. You can use different antennas. You can use directional antennas. You can do a certain amount of things, but inducing attenuation areas, either with attenuation paint or attenuation material, can help you in reducing that, right? So if you have to have the density of the network and you cannot do it otherwise, right? Think about changing the environment. So this is the end of the PowerPoints, because by the way, we hate PowerPoints. So I was thinking about just showing this, the CCIE in a little bit more color, right? I'm from marketing, David is from marketing, Brian is from marketing, right? We use colors a lot, so let's talk about CCIE in colors. So in honor of Keith Parsons, hopefully you can see my screen. This is a school somewhere in Utah, and it's just a typical school. I've already made all of the measurements, so it's nice and in line. I've already done all the walls, so we have dry walls. Can you see this? No, you can't see this.
Can everybody see the echo?
Can everybody see the echo?
Okay, so
okay.
They can see it.
Okay, you can see it. So we have just a normal school, right? So let's put an access point in a corner. And because we are designing for the network, we say that in the school they will have to have good connection. It will be predominantly data. Let's just say the arbitrary -70. That's what we're looking for. So we want our devices to associate with this area, right? Now, speaking from the perspective of CCIE, this is not where the CCIE domain is, right? Remember, it's not about the data rates. It's not about what you said. It's about the preambles. And when we're setting out the information, let's say in the OFDM, the contention will be like this. Right? So any device on the same channel in the area, both the green and the grayed out area, will be able to detect and then defer from the channel. One thing to note is what you see is the perspective of a zero gain client. So if you have an access point with an additional antenna gain, right, this will actually be plus the antenna gain. So it actually furthers the contention, right? So, Brian, so is this the contention domain?
No, this is not the contention domain, because you have to worry about the overlapping cells of the client devices that are going to be part of that service set, and they're going to extend that out. So if there were clients in the same room, probably it'd be a smaller cell, and that wouldn't affect it. But the clients that are farther away that have to contend with that in other rooms down the hall and across the hall, they're just going to extend that contention domain even out farther.
Okay, so let's visualize this, right? I'll just use the access point. Access points are stations just like the clients. And I'll put one access point in room 135 because this is still the signal that we like.
But you're pretending this is a client.
This is a client, right? So let's just pretend this is a client. We have one access point, and this is a client connecting to that access point. And there was enough signal from the access point here and enough signal from here, right? So pretend that this one is the access point, and three of here, they're the clients, right? So one thing that we all know that we have to do is, number one, the access point, we set up the access point power to a lower level, depending on the type of implementation, depending on the application and everything. This is adjustable, but let's just put 15 milliwatts for the access point. Now, we all know that the clients are not as powerful. If you have zero gain, let's say iPad or iPhone, they send and use the TX strength of anything in between 7 milliwatts up to 25. So let's adjust this. $25. And the last one. Okay. Uh-oh. Let's delete that one. I don't like this one.
Somebody added a rogue.
Yeah, that's a rogue access point. Take it. Delete. And let's also, come on, edit, and do this at 25 milliwatts. This is the contention domain, right? We can see that with one access points and the clients on the edge of whatever the data rates we're setting, the all contention domain, well, it's huge, right? With this topology, now this is obviously 2.4. You can see the channel is 1. You could set 3 channels. They would not be overlapping, but you go just slightly over the number of 5 or 6 access points, you'll have co-channel interference. Now, notice one thing, that most of these walls are just dry walls, so obviously the result may differ if you have more walls with more attenuation, but still, right? You can appreciate just how big the contention domain actually is. So, David,
how would you control that, Gregor?
How would I control this? Well, one thing to remember is the client behavior. The signal strength that the client is operating on is dynamic based on the data rates. The further out they are, the lower the OFDM data rate, the stronger the signal would be. So one thing is, if I had this client here, and the same here, and the same here, not only, come on, boy, not only will the contention domain shrink just because the cell size, but also
They've reduced their power.
They will reduce their power. Right? So data rates, the high data rates, high OFDM, or even with the end like 256 QAM, will significantly reduce their power. Right? So just by shrinking the cell size, shrinks the CCI. But still, hey, that's a big cell size, right? So what can we do to further shrink the cell?
Let's control the environment.
So how about the controlling of the environment? Right? One of the things that is very easy to do is thinking about the placement of the access points, right? So usually your access points in the school environment and that kind of environment. Hey man, what's up? That's cool.
We're close.
We're close. So in school-like environment, the most access points are placed on the ceiling, right? So one of the things that I like to recommend is the placement that we all learned from the high-density deployments, right? Either setting them on the wall at the waist level, or even if you have the raised floor, do the picocell deployment.
Why on the wall? For people?
Be on the wall because of the people, right? So if you have this on the wall, and I know that Keith and Yusi, and they know how to use the alcohol. I don't know how to make this lower, so I'll cheat a little bit. I'll just add on attenuation area. I believe this is this one. Human crowd. And if we have the full room of students, right, they're a natural barrier, right? And if we have another room here and another room full of people, you can see that we're shrinking that cell even further. So by lowering the access point, the signal has to go through many bags of water, we're also reducing the contention domain.
Bags of water.
Bags of water, yeah. It's Star Trek. They're recording. Right?
What if they're drinking beer?
If they're drinking beer, they're probably attenuating even more, so that's good.
It's better than my high school.
Right? So Brian, what else can we do?
You can, like you said earlier, older site surveys and things were done to work against the infrastructure and to push through walls because it was just for coverage. But now, instead of just working with the walls and things that are there, you can create the environment like you were saying before. Add things like whiteboards or move filing cabinets around or like the mesh you showed.
Yeah.
So you can just add in another attenuated barrier.
So one of the practical way is a lot of schools, they have either the whiteboards or they have that projector screens, right, that lowers. You can attach the mesh up to it, and it will be attenuator. The mesh is easily 20 dBs, and you can do more. So if you just attach the mesh to the screen,
oh, you're just talking in the back of the screen.
we're just talking just talking about the back of the screen. Look what happens, right? So I think that per screen it would cost about 40 to 80 euros, or what's that? Even if it's one of
we're in America, dude.
Bucks, 100 bucks, right? You can see quite the drastic effect of introduction to that. Now, obviously, this is not your cheapest of solutions, but it's something to be considering when you have to go with the density, right? Now, with the density in the schools, even now, I don't know how are the states. I guess the guys here can comment this, but in the regions like Netherlands or whatever, with the spacing of one access point per couple of classrooms, you can get close to 200 associations per access point, right? So we're talking about very dense area as it is now. How about in a few years with all of the Internet of Things and all of that scary stuff, right? So we have to understand that we'll have to do something in addition to just positioning to allow for a denser deployment, just to cater for the needs, right? And the needs are not the speed. We're not talking we have to carry multi-gigabits of traffic, because that's not it. It's just reducing the contention domain so everything plays as is. But look at the coverage here, right? Now, you could put, what, 6, 8 access points on 2.4, and it would work nice, right? So, any questions? No questions. So either you knew all of these things, or you're just sleeping. Could you repeat that question, please? Yeah.
How did you change that to neg 87?
I changed it to 85. For OFDM, it's the minimum required sensitivity to decode 6 megabit per second. That's 82 plus 3 dBs. That's per standard, so minus 85.
85. Okay. Thank you.
Yeah. Welcome.
What have you guys been doing at night? Where'd the cowboy hats?
Cowboy hats.
You're in Dallas, right?
Where are the cowboy girls?
Dallas Cowboy cheerleaders.
Yeah. So, jokes aside, right? Using Ekahau or any other planning tool is also a great way. to visualize. Something like a contention domain is easy to understand, right? Don't go hang up in just thinking about the data rates, thinking about, even if you understand the contention side, make sure that you understand it's not the perspective of access point, it's the perspective of all of the stations within that cell. It's dynamic, right? One can advertise at single time, and it's dependent on the client population. Now, the good thing is the predominant devices, Apple iOS devices, Androids, and everything else are increasingly becoming better at behaving in the high density environment. So it makes it easier. So still, it's a hard work if you want to deploy high density with reducing. You can never completely reduce the CCI, but you would aim to minimize it as much as possible. Physical, Mac design, and just use the imagination.
So I have a question. When you're surveying an environment with APs already existing in there,
when you're surveying an environment with APs already deployed, what mechanisms do you use mainly to detect that CCI is present in the environment? Is it mainly just retries?
Exactly. That one is the easier, right? Because if you have the existing environment, you can look at the behavior on the layer 2. These are the retries, these are the CRC errors, these are everything that you can gather from all of the network. You have the client counts, and you can just calculate the health of the network, right? So it's much more difficult to see what the effect of the CCI is when there is no network around. So just look at the metrics, look at the layer 2 retransmissions, CCI errors, CRC error counts.
I'm just curious if there's anybody out there that has